So first of all, I also would like to thank the organizers for giving me the opportunity to present here. It's an honor and it's a wonderful workshop with seeing all this progress here. So in this talk, I'm going to present a new bi-alkali species that we have been cooling and transferring to the absolute polar ground state. So it's lithium-potassium molecules. And this work has been done in my group at the Center for Quantum Technologies at the National University of Singapore. So, well, with this audience, I hardly need to really say much for a motivation. Let me just give you this slide that very long time ago when we started this project, we thought, okay, lithium-potassium is a nice idea because it has a relatively large permanent electric dipole moment among the bi-alkalis. It's also a bosonic species. At the time, we were expecting long lifetime of Feshbach molecules. In particular, it's also a Fermi-Fermi mixture. So for the lithium-6 and potassium-40 cases. So at the time, there were also proposals about observing in mixtures breached pairing quantum phases that might be possible to explore. This is really long time ago. At the time, we didn't know anything about chemically reactive collisions and loss from such molecules. Also, for the experimentalists, it wasn't easy to get laser power such that you would make large fermionic lithium or potassium samples. So we actually have chosen at the time to have a third species. So we use a standard rubidium BEC, throw in relatively low amounts of the fermions and do sympathetic cooling. And subsequently, after arriving at quantum degeneracy, start with Feshbach association. And then this talk is then about going to the ground state. So here is just then the paradigm that was set long time ago in the KRB experiment. The Feshbach molecule was an electronic spin triplet dominated Feshbach state that needed to be transferred to a ground state in the singlet potential. So then the solution that has been then afterwards picked up by many other bi-alkali experiments that have been going to the ground state is to seek out an intermediate excited state where that would be of mixed nature for singlet and triplet, so that that transition could be done. So inspired by this, we looked at our case for lithium-potassium. So here is the ground state asymptote. That would be the potassium excited state asymptote. And it looked particularly promising to say, why don't we work near the threshold here, where spin-orbit coupling surely will produce many of those mixed states. And if we address then the B-singlet pi potential at the inner turning point for this weakly bound states, we are not too far away from making a ground state transfer possible. So we started doing spectroscopy there a while ago, observed many lines, and then there was also concurrent work on photo association spectroscopy of the lithium-potassium mixture in the Paris group, in Christophe Salomon's group, and then in a collaboration with Olivier Delieu, they made a Kapitschennis calculation to really sort out and assign all the lines to the proper spin-orbit coupled potentials. And then, as per extension by Leroy Bernstein formula, we were able to also sort our lines that were slightly more deeply bound. I would like to take the opportunity that all these spectroscopic efforts, certainly for lithium-potassium, but also for other bi-alkali species, I do believe greatly have benefited from pre-existing spectroscopic work that was particularly done in the local tradition of the institutions here. So in heat pipe spectroscopy, lots of data have been available to kind of really understand the structure here, but also the ground state structure, or the structure of the ground state potential near the bottom was kind of already pre-researched, and we really have been benefiting a lot from this work. So we were actually able in the end to combine all these available data sets of these 3 papers to create one potential curve that's almost fully empirical, meaning that all the vibrational states, a part of 1 or 2, are actually known for this potential. Anyway, we were not able to use this scheme as a ground state transfer, mostly for the ground state transfer, mostly due to the lack of enough laser power on this transition. And we started exploring something else, something that we now call this singlet pathway to the ground state. So we were addressing low-lying states in the A singlet sigma potential. That would be the idea here. So we started doing excited state spectroscopy. Here's a typical loss line once we hit one of these vibrational levels here. And these levels were also easily identified by mass scaling of previous heat pipe spectroscopy data. So the level spacing there is about 4 terahertz, and we were with the mass scaling off by not more than 10 gigahertz at most for 7 levels that we observed. Then you see that actually we have a relatively large excited state line width here of about 6 to 7 megahertz. That's consistent with our, let's say, humble ab initio calculations, where we look at the hyperfine interaction, in particular the nuclear quadrupole shift that we would expect. All this is expected to be small for the case of lithium potassium, so the hyperfine structure is not resolved. So that would not necessarily point a good prospect for a coherent STIRAP transfer to the ground state. And we wanted to kind of already start with, let's say, preemptive measures. So typically in lithium potassium, the Feshbach states are actually, all the resonances are narrow. So we look at the closed channel, and due to the mixing of the ground state hyperfine interaction, the Feshbach state is typically a mixture of the low hyperfine components in the weakest bound vibrational state of the singlet potential, and in superposition with that, hyperfine components of the weakest bound state in the triplet potential. So in our case, actually, we can apply the asymptotic bound state model that just assumes for these weakly bound states the hyperfine interaction of the atoms throughout the whole range. And we can, in a relatively simple fashion, estimate that actually we have a singlet component of about 52%. So this is what we then use to project up to the A singlet sigma and go down back to the ground state here. So one thing that we did is we went actually by pre-selecting our atomic F and F states in a way that we have stretched nuclear spins. So in an uncoupled basis here, we would fully stretch down the lithium and potassium nuclear spins. So that actually, for the singlet component, the nuclear spins cannot trade a quantum projection quantum number, and there's actually only one sole component that contributes to the singlet admixture of this Feshbach state. So then we can actually excite this and go down. And well, since j equals 0 to j equals 0 transition is forbidden, necessarily the excited state must be actually the rotational 1 state. So the rotational 1 state then has its own projection quantum number that you would in principle be able to trade then with the nuclear projection quantums due to weak spin nuclear spin rotation hyperfine interactions. But if we would use sigma minus polarization, we would just stay in the stretched state. So we would go to the fully stretched state also in the excited state, then use sigma minus polarization on the Stokes transition to go back down to the ground state, again, a fully stretched hyperfine state. So that creates actually a closed system for STIRAP that's just consisting out of ideally 3 levels. All right. So then here would be our two-photon spectroscopy that would identify the ground state if we apply sigma minus polarization. If we change the Stokes to sigma plus, this will not happen because there's just no state that sigma plus can couple to once we are in this excited state. And to support that whole story of the rotational excited state, that we also found the right excited state that is not really perturbed by anything else, here you see that we can address, actually, due to selection rules for the rotational transition from the excited n=1 state, we can go down to the n=0 ground state or to n=2. That gives us a measure for the rotational constant of the ground state, and the first rotationally excited state is expected here and is not observed. All right, so STIRAP then at first really didn't work. That is a best shot after many tries of also trying to get on top of pretty noisy data. We never really had a good transfer efficiency. So the first thing you might say, well, if you do on-resonance STIRAP, you might have the wrong polarization. What is if you're not perfect sigma minus polarization? So we modeled this with about 1% spurious polarization. We have looked at the transfer probability for various single photon detunings. So if you're doing a very slow STIRAP, then a very fast STIRAP with short times, you're not adiabatic enough. But if you're waiting too long, then essentially spurious polarization will kill you. So we never observed anything that we would expect actually from this plot near to that. So the spurious polarization doesn't seem to be a problem. However, there must be something else that prevents us from seeing something better. It's not our cavity line widths. We lock our laser to our home-built high finesse resonator isolated in a vacuum, etc., as at rather short line widths. So we don't think that that is really the problem. But it was already pointed out earlier by modeling really the STIRAP process that also a pedestal on the spectral density for the laser output, fast fluctuating phase noise can lead actually to detrimental effects for the STIRAP efficiency. So we characterize that, and Yatsenko in his paper actually uses a stochastic equation or a model that would just have as an input the bandwidth of this noise and the effective power in the noise. So you would measure the phase noise integrated over this band, get a total RMS phase noise that would relate to the power that you would have in the pedestal. So we went ahead and measured the phase noise of our lasers, and that is phase noise before. On the left side, you see the phase noise spectral density measured from beating the light that we apply to the molecules with light that is transmitted from our cavity, so that would be filtered light. We then improved this laser phase noise by changing our ECDL diode lasers to long baseline diode lasers. So the longer the distance between the laser source and the reflective grating is, the narrower the line width, and also the more suppressed is the phase noise. So after doing this, we have some improvement. We also saw some improvement in the pointer is gone. We also saw some improvement in the in our RF source, and here's kind of the table of merit. We investigated the ECDLs, but in order to boost our Rabi frequencies, we also have tapered amplifiers, where we see that actually the tapered amplifiers do not contribute additional phase noise to the system. But from the short to the long ECDLs, we greatly reduced this. Now you can plug this integrated phase noise numbers that you would see here on the right-hand side and in the table. You could plug this into this model by Yatsenko. So what does that model do? On one hand, it looks at the adiabaticity of the STIRAP. So there is the excitation rate to the bright state. There is the duration tau of the STIRAP that is here contributing to the exponent that determines now here the probability for a non-adiabatic loss. So the slower you go, the lower is this probability to have this loss. In particular, with large excited state line widths like ours, you would think that you would increase just the Rabi frequency to beat this non-adiabatic loss that you would always have. But actually, if you do so, you actually also increase the contribution of the phase noise. So we plug this in here with our Rabi frequencies of approximately 1 megahertz. And then for Stokes and pump lasers, the integrated phase noise figures that we obtain from our measurements, and you get a density plot like that that tells you about this trade-off. So let's say if you make a horizontal cut here for a particular duration of STIRAP, on the very left you're not adiabatic enough. Then you enter the zone, the blue zone here. Blue is low loss probability, so blue is good, red is bad. If you wait too long, if you increase your Rabi frequencies, the only thing is actually you increase the noise contribution again. So this is before our laser improvement, and this makes kind of quite clear that with megahertz Rabi frequencies, we could not really get good STIRAPs here, but then after the improvement, the plot really looks much better. We also have improved Rabi frequencies, so we can actually work somewhere here at very short STIRAPs with probabilities expected bigger than 90%. But before I show you the STIRAP result, we also did a coherent Raman transfer from the Feshbach to the ground state. So here is a resolved spectrum, and here is some Rabi oscillations for the Raman transfer that already point, since we can observe here 2 oscillations, to a pretty good single pass transfer. But of course, an adiabatic passage is much better experimentally because the pulse condition here might be inhomogeneously broadened for the Raman. So for the efficiency of the STIRAP, then we said, okay, how does this situation look now with higher Rabi frequency? Here's again the plot that we have now that accounts for the loss that we have due to spurious polarization. So we thought that maybe here 10 megahertz, the downwards pointing triangles at about 8 microsecond is a good condition for getting highly efficient STIRAP, and this is what we have. So we have now the full sequence where we start with our Feshbach molecules, the signal drops as we go to the ground state, then we do the reverse STIRAP sweep and recover the signal. And then from fitting our models, we get here now a single pass efficiency of 96%. So we are very happy with this. We looked, just to give you one more property here of our molecules. Lithium potassium is chemically reactive. Of course, we see then relative fast loss with a lifetime of about 5 milliseconds, which is quite consistent with other lifetimes of chemically reactive molecules in the trap. So the outlook would here then maybe indeed play the advantage of the Fermi-Fermi mixture and load in optical lattice before we do the Feshbach association. It's narrow Feshbach resonances, but the zero crossing for vanishing interaction, intraspecies interaction, is easily controlled 1.7 Gauss above the resonance. Then, based on Pauli exclusion, have only 1 fermion per species per lattice site. Well, depending on the filling factor that we can achieve, but we wouldn't have problems with a wedding cake structure of not insulator states, for example, in this case. And then do the ground state sweep with our high efficiency STIRAP, and then possibly go to magic wavelength trapping to get long coherence times on this rotational transition. So we are actually setting up at the moment our magic wavelength laser system. So in summary, we have shown actually a new pathway to the ground state that only involves singlet states. Using stretch states, we create an ideal level system for STIRAP. However, in order to have this level system, you need to control the polarization quite well, which wasn't too hard actually. But due to the large excited state line, we really needed to improve and pay attention to our laser phase noise. Improving this then gave us the high efficiency. I would like to thank my team, that in particular Anbang, Xiao Yu, and Sophia have been contributing a lot to this one. Thank you very much.
Thank you.